guys. Can you see and hear me, please? Tell me.
Yes.
Thank you. So let's start. We have a lot of work to do. In case you didn't notice, I will say it, the announcement. This week we don't have practice sessions. So tomorrow we don't meet for the time series. You only meet me for the research seminar. And hence there's no quiz today, but there's gonna be a quiz in the next lecture, next week, next Friday, on the linear time series processes and models. So both. A little bit about Box-Jenkins methodology as well, the one that you are supposed to cover in that online course and also today. So please be prepared. Today we are going to continue with the same stuff that we didn't quite finish last week, and also move on to modeling, actually, partially to what you are already doing in your projects. But you will definitely learn something new, or maybe will resolve some of your questions today. So let's begin. Last week we considered several important. Does it work? Yeah. Several important linear time series processes, data generating processes, theoretical foundations of the models, white noises, moving averages, and autoregressive processes and their combinations, autoregressive moving averages. And this is the main class of processes that we are going to use in modeling, in univariate modeling, also in your projects. Whatever types of models you end up using, either that ARMA or maybe some of you are already using some seasonal adjustments and so on, they are going to be based on this type of linear processes that ARMA. Today we are going to finish the talking about theoretical properties, even though this topic can be talked about further and further a lot. And we will move on to modeling and consider Box-Jenkins approach, and maybe we'll cross out some stuff out from the classic Box-Jenkins methodology, the traditional one that has been used for years, but now it's been a lot simplified for some reasons that we are going to talk about too. But first, let's recall what we did last time. So this is an example that we didn't have time to cover in the lecture last time, but we did something really similar in the practice session. So now let's really quickly go over it. So this is supposedly an autoregressive of order 2 process because, as you notice, there's a time series xt and it depends on its own previous value. So xt depends on the previous value of itself 1 period before t minus 1 and 2 periods before t minus 2. The maximum lag of itself on which it depends is what defines the order of the process. So we have that xt minus 2 here. This is the second order autoregressive process. That's why it's the second order. Then it's also a random noise and no combinations of previous random noises. So that's why it's only autoregressive, not autoregressive moving average. If there were also previous values of the noise component of the of this thing, then it would be a combination of autoregressive and moving average. But then there's a question, is something missing for this process to be, that means that something missing for this process to be actual autoregressive or process of order 2. What do you think that is? Yes, that would be the notion that the epsilon must be some kind of white noise, probably the weak white noise. Otherwise, the process is not a linear process at all because we don't know what's in the epsilon component. The distribution of epsilon does not have to be specified. right? Because it would be already a very strict definition of a process. Yes, we can talk about particular versions of processes where we also specify the distribution of the epsilon, like say that it's not just a weak white noise, but for example, normal white noise when the distribution of the epsilon in which moment of time is normal, but it is not necessary. But to have a weak white noise there, at least weak white noise, maybe strict, it's going to be even stricter, but at least weak white noise is necessary for the process to be considered really autoregressive of order 2. Then this is a part of when we were talking about stationarity of the theoretical stationarity of the processes, and we know the conditions for the stationarity of autoregressive processes of any order, particular of order 2 in this case. We need to write down the thing that is called the characteristic polynomial, solve it, find its roots, and do something about them. So what would be the characteristic polynomial for this process? That would be that phi of z thing.
1 минус 0,85z плюс 0,48z в квадрате.
Yes. Thank you. So this is the characteristic polynomial. It always starts at 1. The 1 comes from the coefficient in front of the x itself in the current moment of time. And then it is like the mnemonic rule for memorizing this would be like you move everything with axis to the left hand side. And then this is how the signs change of the coefficients. So it's minus phi 1, minus phi 2, and then the time shift here defines the power. So the coefficient, which is 1 here in front of the x itself, comes with the 0 power. That's why it's 1, the constant. Then minus 0.45 z power 1 and plus 0.48 z power 2. We need to find the roots of the polynomial. How many roots does it have? Yes, it always has 2 roots. Well, in general, autoregressive process of order p generates power p polynomial, and it has p roots because we don't only consider real roots but also consider complex roots. So it has complex roots. In this case, we are not going to calculate them. Here they are. Yes, I'm hiding them. So here are the roots. You can check that this is really the roots of this polynomial. What can we judge from them about the stationarity of this process? Stationary, not stationary, unit root, explosive.
Стационарный, да.
Yes, the process is weakly stationary in this case. Why weakly? Because it has a weak white noise there, but even if it had strict white noise, still, this is the condition for weak stationarity, for stability of the mean and variance. The process is weakly stationary because the roots of the polynomial are outside the unit circle. So basically, they are larger than 1, strictly larger than 1 in absolute value. Hence, the process is weakly stationary. The other options would be if there was an exactly plus or minus 1 in absolute value root, then it would be a unit root, or if it's well, it cannot be minus 1 in absolute value, but still. And if yeah, actually, yes, it cannot. And if it was inside the unit circle, so less than 1 in absolute value, it would be explosive process. It might be, for example, several roots, and one of them being inside the unit circle or on the unit circle is enough for the process to be non-stationary. So for the process to be stationary, all of the roots must be outside, strictly outside. Yeah. So the unit root, as I said, is the situation when the value of the one of the roots, at least one of the roots, is 1 in absolute value. That's why it's called the unit root non-stationarity process. And let's see once again why it's important. Yeah, this we don't need anymore. So here is nothing missing. This is an actual autoregressive of order 3 process, right? Here's this condition that epsilon is weak white noise. We are not going to write down the polynomial. It's going to be pretty easy. 1 minus 0.85z plus 0.4548 z squared plus 0.32 z cubed, right? And we are not going to solve for the roots, but here what we have, it has 3 roots. 2 of them are complex, and the absolute value of those roots is approximately 1.05, and the last root is real and it's minus 2.83. So what about the stationarity of this process? The condition for all autoregressive processes and for the autoregressive moving average processes is the same. You write down the polynomial of the autoregressive part, solve for its roots, and see if all of them are outside the unit circle. Okay, there's difference of opinion, stationary or not stationary. Why do you think it's stationary?
Ну, все корни вне единичной окружности будут лежать.
Okay, yeah, so this is really a stationary process because all of the roots are outside of the unit circle in absolute value. That's pretty easy. So no, it is not stationary. It is stationary because this is still strictly larger than 1. Yes, it is close to the unit root. This is pretty close to the unit root. In this case, this is a theoretical process, right? So we know for sure the coefficients. When we work with the real data, we never know the coefficients for sure, right? We only can get estimates of them, and the estimates are random values. They depend on the data, and they also have not only those average values or the actual realizations of the values that we observe or that we get from the data when we estimate the coefficients. But they also have some noise in them. We know that if we change the data a little bit or we get the same data from the same process, the estimates would be different. But if the process is stationary, then, well, yeah, the coefficients at least would be estimated well. Probably, if not, then we are going to get a lot of noise and will not be able to estimate the coefficients well. That works pretty much the same way as in the linear regressions in cross-sectional econometrics. There are assumptions. If they don't hold, we get, well, not well working estimates. Same here. The problem is that the unit roots, sorry, not the unit roots, the characteristic roots of the characteristic polynomials, if we not just know the true values of the coefficients and not the true values of the roots, then we also can only estimate them from the estimated coefficients. For example, you estimated the model, you see these are the estimated coefficients, you estimate the roots. And you get, for example, this. And there is also noise in that root, so it also has standard error, some distribution around its average value. And this, depending on how noisy the data is and how noisy the estimates are, the unit root also, as a function of the, not the unit root, but the characteristic root, as a function of the coefficients and of the data, hence, also is noisy. And this 1.05 on average in the data might be as well like something that is a little bit less than 1, a little bit more than 1. And this can also be visible in the theoretical processes if we run some simulations. So is it really, so yeah, it is stationary. The process is really stationary. But one of the roots, well, actually two of the three roots are close to the unit circle. Is it so bad? Should we expect some trouble from this kind of process? And actually, yes, especially when we don't have a lot of data. For example, here are two cases. These are two simulations from the same process, the same one that we just saw. The one that is strictly stationary, but it comes from a unit from something that is close to a unit root. So a little bit of noise into the coefficients, and we will get unit root there, or maybe even something explosive. And these are two simulations out of many possible variations of how this process could look like in the real data. So if you had just, for example, this first graph, would you judge that this time series comes from a stationary process? That is a question. Just based, because there's no nature of this data, we cannot judge essentially about it. This is a simulation. But looking at the graph,
Ну, может быть, и да.
yeah, well, there are no obvious signs of non-stationarity. That's what we call it, right? No obvious signs of non-stationarity, no trend, no drastic shifts, no change in trends, something like that. There is something ugly in the beginning, this drop down, then jump back. But yeah, okay, if what we say, if we cut down the oldest data, then and when we consider starting like from the 7th of the observation, then yeah, why not? It looks pretty stationary. There is something that looks like a little bit of decline, but that just maybe visual artifact or maybe our property of the eye to see something that is not there really, because we are looking essentially for the signs of non-stationarity, and that might be just visual effect of that thing that there are some values that are below the average level grouped together, and that creates some illusion of decline. However, on average, the process in theory, the actual process that underlines under this data, this data generating process is stationary. And the ADF p-value is 0.06. So it actually does not reject unit root. It rejects unit root on 10% critical p-value, but on 5% it doesn't. So something controversial. And another example is this. This is data simulated from the same process. Now, are there any signs of non-stationarity? At least one. It's like the obvious.
Ну, соответственно, разброс увеличивается сильнее
Yeah,
со временем.
non-stationarity invariance, probably, yes. So it looks like it's kind of oscillating a little bit. So it might be, even if it was a longer sample and we saw this the continuation of such behavior, we would maybe imagine that it might be an explosive process even, not just a unit root, but explosive. And the unit root is not rejected here, and not rejected well. So this is pretty huge p-value for ADF test. So this would be a situation when we say, okay, we even might be interested to run a KPSS test to double check, but there's really nothing to double check because whatever KPSS says, we say, okay, so there might be no single trend, but ADF does not reject pretty well, so it is safer to consider that this thing is coming from non-stationary process. This data comes from non-stationary process, even though the actual process is stationary. So this is the problem and it is always like that, working with real data and not knowing the actual thing, and we never know the actual thing that generated this data. So this is something that you should keep in mind when you work with your data. And when you get this awful, as you say, that the results of stationarity test is awful, can we change the data? No, you cannot. And if you now think that I am talking about just one particular team out of yours and picking up on you and maybe being too sarcastic or something, no, because already like more than half of the teams asked about, can we change the data, please? Our data is non-stationary and no transformation can change it. No, you cannot change the data. Just look at this. This data comes from a perfectly stationary process. Well, not perfectly stationary, it is very close to unit root. So yeah, that happens. It will always happen. Worse things can happen. At least you don't have structural shifts. That's good. Maybe some of you have, unfortunately, because now all of you, or almost all of you, have 2020 in the data, and that was a major structural shift for every field in the economics. We cannot just throw that away. We have to learn to work with that. So let's do that. So please stop asking questions about can we change the data until you at least get some reasonable or unreasonably bad results of prediction. Then we can talk about it. But so far, keep working and keep in mind that no diagnostics and no inference methods, no testing and so on is going to perfectly reveal the actual properties of the processes. Even when the processes are good, you are going to get something really strange from the results of the tests, because tests are not perfect as well. Okay, this is the theory of ARMA that we considered. The question still, there is a question, why do we need ARMAs and why we even use ARMA processes and ARMA models? Why they are so important and why we say that this is the baseline or the benchmark model in univariate modeling and prediction, and why don't we use, for example, something more complicated at once? So there's a reason for that. This is the last bit of theory that we will consider about the linear univariate processes. I already talked about it really briefly. Let's look at it now a little bit more in more detail. This is the so-called linear representation theorem, and this is a very powerful result. We are not going, of course, discuss the proof of it. You can look it up in some hardcore time series textbook, but not even all actual university textbooks on time series give this proof, because, well, this is something really complicated and might require a lot of knowledge beyond typical probability and statistics university courses. So this is called the Waltz decomposition or linear representation theorem, and it says that, and this is not about the data or anything, this is about theoretical properties. So that's why it's a theorem and why it's also so powerful result. If you have a process that is weakly stationary, so not even strictly stationary, a weakly stationary time series process, then it can be represented as something like this. So something really strange because it has some infinite order here, and the dependence on the not observations, but on some values of the process that come from very, very, very distant past, so infinitely distant past here. But still, it is a linear representation, so all the components come here linearly. Those coefficients psi are constants. They are not random variables, so these are constants. So this is just a linear combination of some random variables. And the component dt is just some deterministic component. It might be a constant, it might be just zero, it might be something that depends on some values that are determined by the moment of t, by some other realizations, but up to the moment of t, it is a constant of some kind. It might change over time, but change only deterministically, nothing random there. for purely stationary ARMA processes, it is going to be always 0 or a constant. And then there's this, not exactly, you see that this is something kind of epsilon, but I intentionally used that other letter here, or other symbol for the epsilon component to distinguish it from the regular white noise that we have in the ARMA processes, because this is something going to be something different than that white noise that we use there. This is what we call the Waltz innovations. This is a weak white noise of some kind with some parameter sigma epsilon, which is called in this case the innovations, or the process of innovations. And the property of it that it is this something, and there is also another mathematical property, but we can think about this. This is in quotations because this is an interpretation of this property. The coefficients psi are first causal and recent. Not casual, causal, sorry, causal and recent. So it means that they are determined, they are constants, and not only they sum up to something finite, the infinite sum of the coefficients squared is finite. Not only this, but also this summation, it kind of, if you cut it, it is not written there because it takes a lot of space to write it down. If you cut it, for example, started not from 1, but from something older, so you only can see the tail of those of those coefficients, like starting from some distant moment in time and to the distant past. The sum will decrease dramatically. So it's kind of like if you consider the distribution or the weight of those coefficients, even though the distribution over time, not the statistical distribution because they are constants, the distribution of those coefficients over time, the most mass of those coefficients, or the most value combined in those coefficients, it is contained in the recent moments of time. So it is somewhere close to the j's equal 1, 2, 3, and so on. So basically, this coefficient is decreases as j j increases. As you go further to the past, the dependence on the very distant past is lower and lower and lower and lower. Basically, at some point, intuitively, we can say we can cut this tail at some point without the infinity here. We can consider something else. We can always pick a point and cut, and the dependence will be finite. And when we do that, for example, imagine that we did that and we cut it here, and it's not infinite now, but something. What the process would become then? It will be some kind of moving average, shifted by the deterministic component, but just a kind of very, very long moving average. But in general, it is something like an infinite moving average. Not exactly, but almost. And then we can say that, okay, let's cut it, and this is going to be at least approximately, because the coefficients are so small in absolute value and even squared that, well, we can disregard them. This is how it works in practice, and this is the main basis for the Box-Jenkins methodology. If any process has this representation, and we can cut the tail of those coefficients and get something that is very, very close to the original representation, then this moving average or process of high order can be represented as some ARMA. And that's it. This is what puts that all so simple ARMA processes in the picture because of linear representation. Well, where to cut it, to what is the optimal order to represent the process, it depends on the actual process, on its properties, and so on. And this is the big question. So there's not a unique answer or how to represent a given process with an infinite moving average, or especially with ARMA process. And these coefficients, they can only exist in the theory. You cannot observe them from the data, of course, because this is infinite series, and in data you can only observe finite things, finite samples and finite things. But based on this result, the guys Box and Jenkins, they came up with this methodology, which is justified by that linear representation and that possibility to represent each process as a infinite moving average, and then cut the tail and represent the remaining part as some kind of ARMA. And you already should have covered that in the online course, and you already started writing about that and even applying. Some of you started applying this in your homework assignment and in your projects, and also reported some results in your drafts. Which is the case. So what you need to understand about Box-Jenkins modeling approach, that it is not an exact algorithm. Sometimes in all the textbooks and in courses that are based on those all the textbooks, it is still delivered or like shown as an exact algorithm. It was never an exact algorithm. Just they suggested this methodology. They never said that it must be done like that. There is no unique justification that it must be done like that. They said it could be done like that. It is reasonable to do it like that. See, it works if we do it like that. But there's no guarantee that it will not work if you do it some other way, including there's no guarantee that it will not work better if you deviate from that plan. So, and a lot of traditional, like a lot of parts of that traditional algorithm, that traditional approach, were dependent on the context under which people had to work with that. Especially that the samples were quite short, usually, and not everyone could afford estimating a lot of different models and running automated diagnostics. So a lot of stuff, a lot of things must have been done manually or with considerable computational effort. So basically, the computers were weak to estimate a lot of models, or not everyone had them enough. So that's why the algorithm was like that. So the general idea, the general idea that is justified by that linear representation and a lot of practice done over a lot of years of application of that approach. The general idea of this modeling technique, and this is very important, this is what you should basically do in some variation in your projects, in your homework assignments. So that when you have a sample from time series that comes from a stationary process, so you judge about that it comes from stationary process because you cannot guarantee it ever. But you decide to think about a time series process or data that comes from a stationary process, or you justified it with some analysis, including visual, essential tests, and so on. So then it can be modeled, quite precisely modeled, as some ARMA model of an order PQ, and such that the order is not too high. And this is like exactly like it is usually said. Well, they don't use the quotation mark, but they say that basically we can pick order that is not too high, so it is not doing too much overfitting given the sample size. So if your sample is has 50 observations, for example, then not too high order would be well, something that P and Q sum up not more than 10, for example, usually. Maybe a little bit more, but most likely not. And uh, if your data, for example, is from annual frequency, then not too high would be probably something like, well, the order PQ will sum up to 4, 5, maybe 6 at most, depending on the how data is complicated. So not more. If the data comes from a more high frequent data, for example, like intraday observations from a stock market or some other thing that is intraday, when during a day you receive more data and you understand that there's more interdependency over time. So because you take intraday observations and the values today still kind of are correlated or dependent on what happened yesterday, and it was not 2 periods ago as it was in annual data, because 2 periods ago in annual data is 2 years ago, and here in intraday data like 20 periods ago is just yesterday if it's hourly observations, for example. and there is still dependence, then yeah. But you usually have long samples, like hundreds and hundreds of observations, and then not too high order would mean, well, probably something around couple dozen, so 25 or something like that, maybe even less. The less, the better, of course. And then the other, sorry. And the other property is that the residuals will resemble white noise. We cannot say for sure if a process comes from weak white noise, because weak white noise is a theoretical construction, like the distribution. We never say that the residuals in a linear regression in cross-sectional econometrics come from normal distribution. We can make this assumption, we can test it in the data, but we never say that we're sure. We either reject or don't reject. The same here. We say that, okay, in theoretical processes, that random noise component epsilon comes from weak white noise. This is an assumption. We estimate model, we test it. If it doesn't hold, then well said. It doesn't work. We have to change something. Make some corrections in standard errors probably, because our residuals in the linear regression. Oh, sorry about that. Because the residuals in our basically linear regression just auto-correlated for some reason. Or we can change the order of the model. That would be the right thing to do, because obviously we did not account for all the dependency across time between the observations. And we can change both P and Q, make it larger so that the residuals are weak white noise, or like look more like weak white noise. And to do that, we can run tests, of course. And you actually are familiar with those tests. At least you mentioned them in cross-sectional econometrics, because you considered how to evaluate whether residuals are autocorrelated or not. And this is basically that test. So at least something you know about that. At least I guess you used Darwin-Watson statistics, maybe. This is not the best test to apply to time series data, but it is something, and it's definitely the idea is about that. So what we do if we follow the Box-Jenkins methodology, and this is what you should do in your projects, and you already started doing that, some of you already started, but maybe spending a little bit more time than required in the very first steps, and not paying enough attention to the second or other steps. Also, now, if you already considered and if you already saw those lectures in the online course, now please try to maybe restore in your mind what you saw there and compare, because that course, it's not a bad, it's okay, but they present more of that classic traditional algorithm. They pay too much, in my opinion, too much attention to those details that are not necessary nowadays. They are justified by traditional approach, but these days we can afford ourselves not to go so deep into the analysis of the autocorrelation functions, for example. We have to consider them maybe once to determine the maximum order, for example, of the models, but not to try to distinguish the actual order of the process that is going to be the best for our data. That we are going to discover based on the criteria, on statistical criteria that are important. And the most important thing is that the order should be enough for the residuals to be resembling weak white noise. So the first step in the algorithm, as I said, that because this is about application of ARMA, and ARMA are about stationary processes. So we need to get data that comes from what we think is a stationary process. For example, if our data was non-stationary, then we have to transform it. And in the classical approach, in the Box-Jenkins methodology, it was called Box-Jenkins, the full name was the Box-Jenkins ARMA methodology, autoregressive integrated moving average, because they only considered one kind of transformation. If you have non-stationary data, difference it. If it's still non-stationary, difference it. If it's still non-stationary, difference it. If it's still non-stationary, difference it. If you run out of data, well, we don't know what to do. There are no other transformations, only differencing. That's why these days, basically, ARMA as terminology is almost obsolete. Because, well, sometimes we still use it because this is a kind of model ARMA, but actually it is just ARMA for different data. And there are other transformations than difference. And technically, if you apply percentage change as stationary transformation to your data, you cannot call your model ARMA already. It's ARMA for percentage change of the initial data. If you have log differences, then technically your model is ARMA for logged data, but basically it's just ARMA for log differences. So that's why we don't use anymore ARMA in the name of the algorithm. So just Box-Jenkins methodology, and first you get the data that is tested as stationary, tested not based only on the formal tests, no, tested in the general concept, like from essential analysis, from visual analysis, and from the tests. And basically the data that you think that come from stationary process, or you can justify it somehow, that it is reasonable to at least work with this assumption that they might be from stationary processes. It is reasonable for some case. Then you study the process, the stationary process, the data, and you define somehow the maximum order of P and Q for the model ARMA. How to do that? Well, that's typically the rule of thumb that it is not going to be larger than 5 or 6 if your data is of daily or lower frequency. For daily, weekly, bi-weekly, monthly, quarterly, yearly data, most likely 5 or 6 will be enough. If it's not enough, it's going to be seen in one of the further steps, and then you can increase it. But you cannot increase it too much because it cannot take like the most portion of your data. If you have only like 20 observations, which normally people don't work with predictive models with such short data, but then even 5 or 6 is too much. Maybe 2 or 3 is what you have to do to work with. And if it's not enough, then you have to admit that you don't have enough data to work with, unfortunately. But if you work with intraday data and you have like 12 hours observations coming each 12 hours, or like 4 hours hourly, and even intra-hour, for example, or more frequent, then you have to consider, of course, higher order, a lot higher. Sometimes if if your observations are from daily frequency, but you have not as in most economic data, you don't have 5 days a week, but 7 days a week it happens, then probably 7 or 8 is appropriate order for your data. But then again, you have to get more data and so on. So the maximum order is usually determined heuristically. If it's not enough, you just increase it and go back to this point. Then you fit ARMAs up to that order. How to fit? Well, that fit means you estimate them. How to do that? Well, there are several estimation techniques. We are not discussing them even in this course. Basically, we're just applying what the software suggests for us. The typical estimation technique of ARMA is a combination of least squares and maximum likelihood, or conditional maximum likelihood, actually. And there are other names of it, but basically this is just first you apply linear, not linear, the ordinary least squares to estimate just the autoregressive parts. You use the coefficients as the starting values for numerical optimization for maximum likelihood, and then you optimize them. This is the algorithm that is proved to be close to the efficient full maximum likelihood estimator. If the process is stationary and if it is far enough from unit roots. Sometimes when your process is close to unit root, on this stage you will get the coefficients are estimated, but blah blah blah, something close to unit root. Be careful, blah blah blah. Don't do that, and so on. So these warnings are already like fit in into the software. The software will very nicely and kindly inform you that you are in a dangerous position regarding the unit roots. If you get the coefficients that give you unit roots inside, not unit roots, give you unit roots or roots of the characteristic polynomial that lie inside the unit circle, you will be notified. So your autoregressive part is not stationary. And when it happens, you will not be able to finish the estimation. Basically, that means that this order is not right, or that this order is not right for your data, or that the data is not good at all. So basically, you made a mistake thinking that it is stationary, because no stationary process can be fit to this data. Okay, so if you decided, for example, on some maximum P and Q, how many models will you have to estimate? This is a question. So you are using ARMA PQ, your maximum order are like, say, P hat, Q hat. How many combinations of ARMA fit to this maximum order?
P плюс 1 умножить на Q плюс 1.
Yes. This is how many specifications you will have to estimate. Y plus 1, because there's also this. Wow. What is this model actually? Yeah, nice. 90s has come to Prague. Welcome. So what's the model ARMA 00? No, it's not a hard question. So autoregressive part is 0, so there's not going to be any dependence on the previous values of x, right? There is still a constant, because the constant appears there independently on whether there is dependence on x or not. And the moving average part is also has 0 order, then there's not going to be any dependence on past values of the randomness. So this is just this. Yeah, that's behind me. There's epsilon comes from big white noise. So this is ARMA 00 is basically a shifted white noise, shifted by constant. We can even say what is the best estimator for this model. Can you say right away what's the estimate for the coefficient is going to be? The model has only one parameter of the coefficients. There's also another parameter that is the standard deviation of the white noise, but the parameter of the linear model itself. What is the estimate of it? Doesn't matter whether it's maximum likelihood or least squares or whatever. Yes, come on, you saw it like a million times. It left marks on your brains.
Средняя по ряду.
Yes, that's just the average, sample average of the time series at your disposal. And this is a pretty important model, so please don't disregard it. When you consider predictive power of your models, And if it happens that this model is valid for you, so when it happens, because this is a very strict model, you see that basically it says that this guy itself is not autocorrelated. This is the assumption of the model. When you try to estimate it, you say that, okay, this is a constant plot plus just something that is not autocorrelated at all. So when you don't see any autocorrelation in the X itself, this might be the model for your data. Well, it is not really a good model, probably, but why not? If your sample is very short, it might be quite reasonable. It is especially important in the light of predictions, because this model gives you what we call the naive predictor. The naive predictor, one of the naive predictors of the ARMA type, when you just predict from a constant. The predictions for the future values of the stationary time series is just a constant based on the average level in the past. So this is the naive predictor of the linear type. Okay, then there are other models that are just pure autoregressive parts. Those are ARMA P0. There are pure pure moving average models that are ARMA 0Q. And there's also ARMA, which is PQ for P and Q non-zero. So this is how you get P plus 1, Q plus 1 models to estimate. And even if this is 5 or 6, you get that if it's 6, for example, then P plus 1, Q plus 1 is 7, then it's 49 models already, so almost 50 models. And that's quite a lot. So that's why people tried before, in the past, people tried not to estimate everything and then see what fits and what doesn't fit and throw away what is not working. Now we can do that, because even when the samples are long, the estimation of an ARMA model is a pretty simple routine operation. It doesn't take a lot of time like this, even for high order. So it's okay to estimate a lot of models and then see what fits and what doesn't fit and throw away what doesn't work for us. So what we do, how do we understand what to throw away and what to leave to work for? The first criterion is the residual autocorrelation. So you test all the estimated for the residual autocorrelation. And I asked you the last time, I asked you to pay attention to do this in the online course. So what would be an appropriate way to test it? So yes, many tests can be used. That's true. Can you name at least one? Yeah, this is nice now. I expected this reaction, even though at least 2 teams already used those tests in their like draft of the reports, already reported some. Do you remember what you used? There was something abbreviated like this. Ring some bells? Does it ring some bells? Okay. So the question remains, which tests will you use? The online course suggests, yeah, LB test, but what is it? This is the LB test. This is a longer name of it, which is the same test. S stands for statistics. Okay, QS stands for Q statistics. It doesn't have longer name. B stands for box, the same box as in box Jenkins. L stands for Lewing. That's the Lewing box Q statistics test. That's the same test that you use when you, for example, when you consider autocorrelations in the first part of the, not the first, the second. If you consider the, you decide to consider the autocorrelation functions, and you decide which at which logs they are significant and not, you use the Q statistics and the Q statistics p-values. And no, the information criteria, these ones, Schwarzer bias or archaic information criteria are not tests for autocorrelation. They are not tests at all, strictly speaking, statistically. These are information criteria. This is a special way of diagnostic tools, special kind of diagnostic tools. You only compare different models to them, but you don't test any hypothesis. And Lewing box Q statistics is something that allows you to test the hypothesis of significance of autocorrelation coefficients. That's why you use it. There are other ways. For example, EViews offers you like a lot of options. In other, you have to choose yourself what you want to use. Well, Lewing box Q statistics is one of them. The null hypothesis, how it works in short, the null hypothesis that particular of Lewing box is that no autocorrelation of particular order, and this particular order must be chosen your own, so it some like 1, 2, 3, 4, 5, and if all are rejected, then yes, it's nice, and not all not rejected, then it's good. So then p-value must be something like what, for us to consider that the residuals resemble white noise. This is a conventional criterion. You reject the null if p-value is something, you don't reject if p-value is something else. Okay, so we are looking for not being able to reject the hypothesis of zero correlation or no autocorrelation, then the p-value must be larger than something like the critical alpha level. Then don't reject. That's why we only choose for each model that we estimated, we estimate the residuals, we apply the Lewing box test, and we only keep those specifications, those orders P and Q, for which p-value is high enough. High one, for example, higher than 5%. If there's no models that give you p-values higher than 5%, then, well, make it 10. The opposite, if it's not enough, then you decrease it. Okay, and the last point here, you pick the one model that fits the data best. And this is the most controversial point of this algorithm, because, well, how do we do it? There are many ways to do that. What are the ways that you learned from that course, for example? Again, some of you already reported some models and even chose some already. how do you pick if some model fits the data? That is not even time series specific econometrics question. It either fits or doesn't fit. How do you understand that? Or it fits well or not well? Or some model fits better than the other ones? Yes, one way to choose the model would be via information criteria, like archaic information criteria or Bayesian information criterion. The smaller it is, the better. And you should not use two of them because they might be giving you controversial results and you will not be able to do anything about it. For working with linear ARMA, it is conventional to use Bayesian information criterion. The justification for that is really strange because in case you work only with autoregressive processes and if the actual process is some kind of autoregression, then the discrimination with Bayesian information criteria will reveal the true order. But yeah, well, we are working not with only autoregressive processes, first of all, and second of all, we understand that our linear processes are just approximations of the actual thing that is going on in the data, and we don't know what it is. So we can also use archaic criterion, for example. But please, in your work, use only one of them. Which one is up to you? It doesn't matter. Sometimes you pick only the one that is best. Sometimes you pick like a top 5, for example, if you have a lot of options and you need more models to consider because you are going to run predictions, and you see that some of the models, for example, have huge information criterion values and some have smaller and very similar, and you can pick the smallest one, but they are kind of look the same almost, but definitely smaller than the other ones. Then you can choose those 3 because they are close to each other, for example. Or if you just want more models to work with, so the smallest ones. What are the other criteria? Well, think for yourself because you know that already. Even some of you already used it, and you know it from the previous econometrics course. What are the measures of some model fitting data or not fitting the data? Because information criteria is not really about the data fit. It's something that allows you to compare models. It is connected to the fit to the data, but not directly. What else? A very important question at this point: what if you work with several different data that represents the same process? For example, you have initially data that is not stationary, and some of you are in this situation. Many of you actually. And you consider, okay, this might be transformed like this might be transformed like that. Or, for example, we could use this portion of the data or that portion of the data. Same data, same process, but different portions of the data or different stationary transformation. And then you have to do all of that for each of that data portions or each time series that is stationary. Right? You do that, you estimate, and then at the end you come up, for example, that there are 10 models that are that satisfy no residual autocorrelation for percentage changes. There are 20 other models that satisfy no residual autocorrelation for something like for second differences of the initial data. What then? How do you resolve the last part? What do you choose? Can you compare information criteria according to information criteria models that are estimated on different data, for example? Can you just estimate information criteria for models that fit second differences, for models that fit percentage changes, and compare and pick the best? Or can you like compare the information criteria for models that fit longer or shorter samples? This is also not a time series specific question. This comes from the econometrics or statistics or whatever, where you learned about the information criteria. So no, you cannot do that, first of all. You can only compare according to information criteria only the models that are estimated on the same data exactly. The same comes to the other fitting criteria. If you are evaluating R squared, for example, but never do that, or you evaluate mean squared error of the on the fitting sample, or some other type of fitting of error that you consider to show the fitting quality. You cannot compare those criteria for the models that are fitted to different data. So if you are working with several time series for the same, several stationary time series for the same process initially, for the same data, for the same task, you will have to do this algorithm all for this for each the data, and for each you will have to pick one or several the best models, and then you will have to compare them based on some other criteria that would be predicting quality already. So then you will evaluate predictions and decide which fits better. So this is the home task already that I asked you to do. You should have studied that approach in the online course. Well, it is now kind of clear that you did not really do that a lot, but that's okay. You still have time. This is the end of this part of the lecture. Now it is actually time to there's some time to talk about maybe what you have to do in your projects, because the next time we are going to cover predictions, and there is also prediction module on your on that online course, and you have to consider also that. And that is going to be it, because there's also one other topic in the course, but that is not a part of the project homework. So now you have all that you have to do, or all that you have to use up to the prediction point at least. And even you can already construct predictions because it's quite intuitive, but probably you are not ready to evaluate the quality of predictions. And some of you already actually constructed predictions, I guess, based on some algorithms. Not really well, but we are going to discuss that next time. So do you have any questions about your projects now?
А подскажите, пожалуйста, вот мы вчера до дедлайна отправили вам проект.
Yeah, I saw it. It didn't come
Да?
on time. Yes, I saw it in the morning.
Мгм.
It's okay.
То есть всё
I
нормально,
will
да?
answer you later. Maybe tomorrow.
Спасибо.
Владимир Николаевич, а можно такой вопрос?
Да.
Вот в описании проекта, задач проекта, там сказано попробовать побольше разных стационарных преобразований и протестировать их, желательно далеко не стандартных. Вот.
Окей.
Вот. А вот если у меня буквально с первого какое-то формальное преобразование, там условно, оно сразу является стационарным, то стоит ли пробовать дальше?
Нет, не стоит. Okay, stationary transformations that we studied. This is strange to have dialogues in different languages, but still. Stationary transformations that we studied, they are studied not just because I picked them up from the floor randomly. They are the ones that are going to be the best way to transform your data in most cases, if there are no complications. One of those complications when those transformations like differences or log differences or percentages don't work is seasonality. If there is no seasonality in your data, then it is most likely that one of those will fit your data perfectly. The other complication is structural changes, but that can be dealt, for example, via second differencing that most likely it's going to kill that. And no transformations are going to kill non-stationarity in variance, but we are not looking for transformations to do that. To model data via ARMAs, we only look for stationarity in mean, first of all. Yeah, it is nice to have uh, stationary in variance process as well, but and if we can, we sometimes, and some of you do that in your homework, we can cut, for example, all the portions of the data if our data size, sample size allows us to do that. Then we cut the older portions to achieve more stable invariance time series, because then we understand that it's going to give us better estimates and more precise prediction evaluation quality. You kind of don't know that yet formally, but you kind of already expect that because this is what your intuition from the econometrics one tells you, I guess. Well, ideally it should be like that. So yeah. And of course, the first rule, the most important rule about stationary transformations is that they must be meaningful, of course, for your data. And when you have seasonality, for example, in your data, seasonal differences is something really meaningful. It makes sense when you consider sales, for example, or sales-related data, as I think two projects deal with that, or even, yes, at least, maybe three, I don't remember
Ну,
exactly.
это наш один, да.
There are at least two teams that deal with that thing, and the same kind of stuff that works like this. December, December, December. Yeah, well, taking seasonal differences is something that is really natural in that case, of course. The same kind of thing would happen if you consider like macro data related to taxations, for example, or if you consider currency exchange rates on monthly basis, or something like ticket sales, or flu cases outside the pandemic times, and so on. Well, why not? So we don't consider seasonal stuff in this course because we cannot fit everything in this course, and there are more important things to consider than seasonal transformations, because it is kind of very intuitive how to deal with them when you know how to deal with just differences and just growth rates and so on. Just take seasonal transformations. Uh, so there's a question: when is the deadline? Which deadline? The final? Ah, that one. This is from the previous lecture. This deadline. This is by tomorrow. It means that by last week. That this is I showed you last week. So it was already last week, this deadline. The module 3 you should have finished by now, and I see that you didn't do that. So you have a week before the quiz at all, and if you wish to do well on the quiz, you have to work on it. So the quiz will contain questions about the properties of linear data generating processes, so that white noises, moving averages, autoregressive processes, random walks, and mixed ARMA. All that stuff that we did. Like here, I did not. Yes, but for example, yes, this is the process. Is something missing? Yeah, this is missing. Write down the polynomial, check if it's stationary. Okay, it's stationary. The next question would be that we covered in the practice session. If it's stationary, then what are the moments of it? Because stationary means that the moments are stable. The first moment is stable, the second moment is stable, and you have to be able to calculate those. The expectation of the process and whether the process is autoregressive or moving average or a combination of those. You have to be able to calculate the variance. You have to be well, at least you have to know how to approach calculation of autocovariance. I will not ask you to calculate that in the quiz for sure, but in the exam, yes, because this is a longer. There is a longer time to do that. During the quiz, for sure, no autocorrelations calculation. So,
Владимир Николаевич, а может
yes.
тогда вот догоняющий вопрос? Вот если у нас данные, господи, сезонные, но обычное процентное изменение, оно сохраняет сезонность, но стационарное. И выглядит стационарным, и, соответственно, тест
Seasonal
показывает,
data
что
is
оно
not
стационарно.
stationary. Seasonal data is not stationary by definition. If it's seasonal, it's not stationary.
То есть даже процентные, ну, то есть даже если тесты показывают, там вообще красиво выглядит.
Yes. Tests show you trend stationarity. And seasonality is a different kind of trend. It is trend, but it is not captured by models that cannot account for seasonal trends, and neither model that is underlying ADF test or DF test or KPSS test or PP test or all those around trend and unit root tests, they do not account for seasonality. Because seasonality is something that you judge on normally, essentially and visually, and then via those visualization tools like those star plots and seasonal not differences, seasonal mean differences in mean and so on. And well, if it is look kind of stationary except that there is seasonality, this is what you mean, I guess. Yes, then the test will show that it is stationary. You will not see any trends or any oscillation or like non-stationarity in terms of shifts and so on. So yes, other than seasonal deviations, every other season or every season there is no signs of non-stationarity. Then you can still use linear models. You will just get that seasonality in all your residual autocorrelation. You will not be able to get rid of it in any ways other than using some kind of seasonal correction. I already told some of you that, yeah, you can do that in your models. You can try seasonal models. It's okay. They are really close to just models. Then you will have to consider more models, of course, because you have to still try to use non-seasonal ones. Or you can just use seasonal dummies that you can that you know how to do even from basic econometrics. Just create a set of dummies that are ones when there's season, for example, that monthly dummies in your case. So 12 dummies, it's okay. If you think that only one of the months is important, like December, as I drew in the graph, then add only December dummy. Then you will have less overfitting and more predictive power probably, but who knows. So in that way you can experiment, but still cover basic models. You can do that. It is not a contradiction to this approach. It's not a contradiction to use it for data that has seasonal component. The problem will be here, because you are going to get something like oh, sorry, what is okay. So yeah, let's use this as a slide. You will be getting something like this in your autocorrelation profile of the residuals every time. So that's, for example, 12 if you have monthly data. So you will be able to get rid of this autocorrelation between the lags 0 and 12, but on the 12th lag you will get something like this. Same kind of thing will happen for daily data for stock market, for example. If there is if there's a considerable weekday after the weekend effect, then each sixth slug you will have this, something like this on the sixth slug. It is a kind of seasonality. You cannot remove it by just considering higher order models, because it's not removed by linear models. To remove it, you have to consider non-linear models, and we are out of that. So this is not a contradiction to that linear decomposition result, because you are trying to model essentially non-stationary data. Well, you still can hope, and you can still even expect your models to deliver reasonable predictions of reasonable quality. But this thing will appear there, and you will also notice that it is affecting your prediction error. In the prediction error, you will see that not removed seasonal component. But at least you know what to expect about that, right? So if you see that there is a seasonal component that is not removed, so for example, each December or each Monday, your prediction underestimates the true value because it doesn't account for that seasonal jump. Okay, you know that, okay, so most of the day or most of the year, the predictions are pretty well, but they are not really working well in December's or in on Mondays because they don't account for seasonal jump in the because they are linear, and we cannot remove seasonal component by linear modeling. Okay, this is still reasonable result because as a user of that model, you know what to expect. You expect the model is working pretty well everywhere but on those periods. And on those periods, you know, okay, so the model predicts this, we should probably expect something better or something worse, because it usually is. Not exactly known by how much, but something. This is not statistical already modeling, but it is still reasonable for a project task. Kind of hands waving, but this is what economists do all the time. And this is like if it was a research project, not a finished work, or a research project where you have to also state what to do next, or what are unresolved issues, this would be one of them. So, okay, this is an unresolved issue. It does affect our results, but still our results are pretty reasonable, and it basically says that if we considered seasonal models, it would be better. Happy end. That's something that I expect from some of you at the end of your homework assignments. Okay, we have used the time now. If some of you still have questions, then please stay and ask. If not, then thank you and see you tomorrow in the research seminar and next week in time series.
До свидания.
А можно спросить, вот вы сказали, что можно с сезонными моделями экспериментировать, то есть с ARMA можно использовать, да?
Yes, ARMA.
С ARMA.
Yes. Well, yes, if you are using ARF, then it is the ARMA function, or ARMA function with seasonal order option, yes. In if use, you will have to use those terms to include into your models. In other languages, I don't know. I'm not sure if Stata has seasonal models by default. I'm sure that it has, but I'm not sure if by default.
Вот разделение на подвыборки мы на следующей паре пройдем.
Yes.
Сейчас не спрашивать, да, поэтому пока
В
лучше.
принципе, у вас уже есть достаточно информации, чтобы это сделать. Во-первых, в онлайн-курсе про это говорится. Во-вторых, я уже всем ответил про это на отчеты, что делить надо и как примерно.
То есть, ну, я же правильно понимаю, что мы акаики считаем на fitting sample?
Да.
А зачем тогда на валидационный?
На валидационные мы будем считать прогнозы. Так, секунду.
Ну ладно.